Welcome to Brain Vision.
So here now, for part A, we can see that the radius of the marble is going to be much less than the radius of the loop. So lowercase r would represent the radius of the marble. Capital R would represent the radius of the loop. We know that the marble isn't slipping. Therefore, we can say that the angular velocity is related to the linear velocity by a factor of 1 over r, lowercase r being the radius of the marble. Therefore, we can say that the mass of the marble times the velocity at the top of the loop squared over r would be equal to the mass of the marble, or rather the weight of the marble. So we can say that the velocity at the top of the loop squared would be equal to g times the radius of the loop itself. And we can say that then we're going to say that due to the conservation of energy, the energy at the release point would be equal to the energy at the top of the loop. Then we can say that the kinetic energy at release plus the potential energy at release would be equal to kinetic energy at the top of the loop plus the potential energy at the top of the loop. And so we can say that 0 plus mgh would equal 1/2 times m times velocity at the top of loop squared plus 1/2 times the rotational kinetic energy of the marble. So omega, the angular velocity of the top of the loop squared, plus mg2r, so essentially plus the gravitational potential energy at the top of the loop, the height being 2 times the radius of the loop itself. So we can say that mgh would be equal to 1/2 mv, we'll just say mv loop squared, plus 1/2 times the moment of inertia of a sphere, so 2/5 mr squared, multiplied by the velocity of the loop squared at the top of the loop squared, divided by r squared, the radius of the marble, plus, again, 2 mgr. We can say that mgh would then be equal to 7/10 times the mass of the marble times the velocity at the top of loop squared plus 2 mgr. We can then cancel out the m's and say that gh will be equal to 7/10 times the velocity of the loop squared plus 2gr. And we're going to say that then h would simply be equal to 2.7 r. Again, this would be your answer for part A. Again, the velocity of the loop squared being equal to gr. So you would plug this into there. The gravity then cancels out, and you have that the height of the release must be equal to 2.7 times the radius of the loop that the marble is trying to go through, essentially. So this would be your answer for part A. For part B, however, we cannot say that the radius of the marble is much less than the radius of the loop, so we cannot make that assumption. If that is true, let's draw a diagram. This would be the loop, this would be the marble, and we can say that if we consider this level to be y equaling 0, we're going to be considering this, the distance from y equals the bottom of the marble, to be 2 times r minus 2 r. So 2 times the radius of the loop minus 2 times the radius of the marble. So we can then say that, again, the mass of the marble times the velocity at the top of the loop squared divided by r minus r equals mg. And so we can say that the velocity of the loop squared would equal g times r minus r. Now, if you can tell, this is all the calculations are going to be the exact same. However, now at the end, we just have to plug in r minus r. So again, we can say mgh equals 1/2 mv loop squared plus 1/2 I omega loop squared plus 2mg r minus r. So that would essentially be the gravitational potential energy at the top of the loop, assuming that, rather, we cannot make that assumption anymore. We cannot make the assumption that the radius of the marble is negligible compared to the radius of the loop. Therefore, however, all of these calculations are the exact same. So if you cancel out everything, you're essentially going to get that h is going to equal 2.7, but instead of equaling 2.7 r, it'll be 2.7 r minus r. So this would be your answer for part B. That is the end of the solution. Thank you for watching.